Right now, as you're sitting there, there's an invisible war raging inside your body. It's a microscopic battle for survival with these incredibly complex strategies of attack and defense. So today, we're going to crack open the bacterial playbook to really understand how this fight unfolds moment by moment. Okay, I want to start with just one number. Look at this, 10 to 1. Just let that sink in for a second. What on earth could that possibly be? Well, that's it. That's the ratio. For every single one of your own human cells, there are about 10 microbial cells living on and inside you. Think about that for a second. In a very real way, we are more them than we are us. It's a staggering thought, right? And it brings up a really critical question.
Are all these tiny passengers friend or foe? Are they helping us out, trying to harm us, or are they just kind of along for the ride? Well, as you've probably guessed, the answer is all of the above. And understanding that difference is absolutely key to understanding infectious disease. All right, so to figure out who's friend and who's foe, we first need to meet the residents. This entire community of microorganisms living with us, that's what we call the human microbiome. It's this incredible, dynamic ecosystem that literally starts building up from the moment we're born.
So our relationship with these microbes kind of falls into three main buckets. First, you've got commensalistic. This is basically neutral. They're living on us, but it doesn't really affect us one way or the other. No harm, no foul. Then there's mutualistic. Now this is the good stuff, a total win-win. They get a place to live, and in return, they help us with things like digestion or even protecting us. But then you get to parasitic. This is when one of them benefits, but at our expense. And that is what we call an infection. Okay, so how do we measure the amount of damage a parasitic microbe can do? That's where this word virulence comes in. It's not just about if a microbe makes you sick, it's about how sick it can make you. A highly virulent pathogen, like the one that causes the plague, is absolutely devastating. On the other hand, an avirulent or non-harmful strain can't cause disease at all. So what gives a bacterium its power?
Well, that brings us to their arsenal, their secret weapons. You can think of these as the offense playbook for bacteria. These are the tools and the strategies that can turn a harmless microbe into a really formidable foe. So what's in this playbook? How do they actually attack? Well, some use these things called pili, which are like tiny molecular grappling hooks to latch right onto our cells. Others build themselves a capsule, this slimy outer layer that's basically an invisibility cloak, making it really hard for our immune cells to even grab them. And get this, they can even change their appearance. It's a tactic called antigenic variation, kind of like a spy swapping disguises. This is exactly why you need a new flu shot every year. The virus changes its coat, and yeah, bacteria can pull the same trick. And of course, you've got the heavy artillery, powerful weapons like tissue-dissolving enzymes and potent toxins.
All right, let's talk toxins, because they come in two main flavors. Exotoxins. Think of these as targeted missiles. They are proteins that are actively fired out by living bacteria. They are highly specific, and we're talking about the things that cause tetanus or botulism. Endotoxin, on the other hand, is totally different. It's actually part of the bacterium's own wall, and it's only released when the bacterium dies. So it's less of a targeted weapon and more of a tripwire that sets off a massive body-wide inflammatory alarm. This can lead to a dangerous overreaction called a cytokine storm, which is a huge factor in what makes sepsis so deadly.
But hold on, our bodies are not just sitting ducks here. We have our own defense playbook. It's this incredibly sophisticated, multi-layered system that has evolved over millennia to counter these exact kinds of threats. Our first line of defense is our innate immunity. This includes the obvious physical walls, like our skin. Then you've got chemical warfare. We have enzymes like lysozyme in our tears that can literally dissolve bacterial cell walls. And we have cellular sentinels on patrol. Phagocytes, which are cells whose entire job is to hunt down, eat, and destroy any invaders they find. And this process of cell eating, called phagocytosis, is just fascinating. It's like a little three-step dance of destruction. First, chemotaxis. The phagocyte follows a chemical trail to find the enemy. Second, adhesion. It has to physically grab onto the bacterium. And finally, digestion. It swallows the microbe whole and just obliterates it with powerful enzymes. It's an incredibly effective system, but bacteria have learned to fight back. And this right here is where the evolutionary arms race just gets intense. For every single step in our defense, bacteria have evolved a countermove. They can block the chemical signals that call for help. They can use those slimy capsules we talked about to make themselves too slippery to grab, and some are so tough they can resist being digested or even kill the phagocyte from the inside. It is a constant back and forth battle.
Sometimes the most significant damage isn't caused by the battle itself, but by the aftermath. Our immune system, in its zeal to protect us, can sometimes cause collateral damage, or what you might call friendly fire. The medical term for these long-term consequences is sequelae. These are conditions that pop up long after the initial infection is gone. And the kicker is, they're not caused by the microbe anymore, but by our own body's reaction to it. A classic example of this follows an infection as common as strep throat. This is exactly what happens with acute rheumatic fever, a serious complication of strep throat. Our immune system produces antibodies to fight the strep bacteria. But in a tragic case of mistaken identity, some of those very same antibodies can also recognize and attack proteins in our own heart valves. The body accidentally attacks itself. So the really key thing to understand here is that this damage isn't being caused by an active infection. The bacteria are long gone. The harm comes purely from the immune system's own misguided, long-term response. And as you can imagine, that creates a real diagnostic challenge. Which brings up the obvious question, right? If a patient shows up weeks later with heart inflammation and their strep throat is just a distant memory, how does a doctor connect the dots and prove what actually caused it? Well, the answer lies in modern diagnostics. You really have to think of it like microbial forensics. The culprit is long gone, so instead of looking for the criminal itself, we have to look for the fingerprints it left behind. And in this case, those fingerprints are the antibody response it provoked in us. And this is the detective's toolkit. You've got traditional culture where you try to grow the live bug. It's definitive, but can take days or even weeks. You have rapid antigen tests that look for pieces of the bacteria, and molecular tests that look for its genetic code. But for those post-infection problems, serology is key. It doesn't look for the bug at all. It looks for the antibody fingerprints our body made in response to it. Let's look at a quick case file. H. pylori, the famous bacterium for causing stomach ulcers. Its secret weapon is an enzyme called urease, which neutralizes stomach acid and creates a safe little bubble for it to live in. We can cleverly detect this with a urea breath test. But here's the challenge. Even after treatment successfully gets rid of the bug, the antibodies can stick around for years. So a positive antibody test doesn't necessarily mean you have an active infection right now. And that really highlights a critical issue here: timing. For a rapidly progressing disease like Rocky Mountain spotted fever, waiting for antibodies to show up in a test, which can take 7 to 10 days, is just too long. Treatment has to start based on clinical suspicion, well before serology can ever confirm the diagnosis. So ultimately, when you look at the big picture, diagnostics is a balancing act. It's a race between getting an answer quickly and getting an answer that's certain. Each method has its place, helping doctors identify the enemy so they can choose the right weapon for that specific battle. And this brings us to our final thought. We've explored the playbook of bacteria and the counter-tactics of our immune system. We've seen how we investigate the aftermath. Our bodies truly are a constant battlefield, and as technology evolves, it just makes you wonder, what other invisible wars are happening inside us right now, and which ones will we be able to see and maybe even influence next?